Hello everyone, it's my great honor to give a presentation on my recent work for this seminar. My name is Zhang, a PhD candidate from National University of Singapore. Today, my presentation topic is a region of strength of calcium silicate hydrate. Well, before I start my presentation, let's look at this picture. It comes from one recent review on the potential research needs for the cementitious building materials. Most of the topics are highly related to solutions to solve the environmental problems. For example, people try to use alternative raw materials to produce clinker for reduction of carbon dioxide emission, or use low cement content in concrete for the same purpose. More directly, the carbon dioxide capturing techniques are also explored in building construction. All of these efforts are to realize an eco-friendly solution in cement industry. However, introducing other phases into cement and concrete will influence its final properties. As a construction material, its mechanical properties is extremely important as it is related to the safety and lifespan of building structures. It is essential to prioritize the fulfillment of strength requirements while designing eco-friendlier cementitious materials. So understanding the strength origin of cement is very important and can provide theoretical support for these research problems. However, cement is a complicated material and there are still lots of things unknown on its mechanical properties, even though people have already used it for centuries. The complexity of cement is mainly due to two aspects. We can see from the SEM image that cement is a heterogeneous material with many phases mixed together. The main phase of hydrated cement is calcium silicate hydrate, which is also called CSH. It contributes most strength of cement. Some other phases, including calcium hydroxide and the unhydrated clinker, are also inside. The complicated microstructure and composition makes it difficult for quantitative analysis. Thus, it is a prerequisite to extract the main phase of cement and well control its chemical composition and microstructure for further study. CSH exhibits a hierarchical structure. At the molecular scale, its structure is widely recognized to resemble topamorite. The configuration consists of linear silicate chains arranged in a specific form. These chains coordinate with calcium ions, creating a kicked pattern that repeats after every 3 tetrahedral. The negatively charged silicon ion layers are also balanced by calcium cations in the interlayer region. These interlayer calcium ions form a strong ionic covalent bond with the CSH layer. This bond allows for the compact stacking of CSH layer, leading to the formation of CSH particles. The nanostructure of these assembled CSH particles, along with the presence of pores, remains enigmatic and subject to ongoing debate. Current popular models include describing the nanostructure of CSH, include the layer structure and colloidal structure model. The layer structure model that the CSH particle exhibits a structural resemblance to a layered topamorite-like crystal. The colloidal model can be noted as CM1 and CM2. In the CM model, the fundamental building blocks is a grain-like particle composed of a few stacked layers. These particles can aggregate, forming globes that serve as a primary building blocks, with a diameter of approximately 5 to 6 nanometers. The difference in CM1 and CM2 is the geometry of the basic building blocks, being as sphere-like for CM1 or brick-like for CM2. At the microscale, the primary difference in microstructure lies in porosity. The hydration product of cement can be classified into inner product and outer product with smaller and larger porosities, respectively. The hierarchical structure results in large discrepancy of strengths in different length scales. From this graph, we can see that the multiscale mechanical properties of CSH exhibit significant size effect. It refers to the phenomenon where the strength of a material decreases as the stress size of the scale of the specimen increases. It arises due to various factors, including the presence of defects, strength concentrations, and limited statistical representation of the material's strength. At larger scales, the influence of defects such as micro cracks, voids, or impurities becomes relatively more significant compared to the material's inherent strength. These defects act as stress concentrators, leading to local stress concentrations and the ignition and the propagation of cracks at lower applied stress levels. As a result, the material exhibits lower strength when tested at larger dimensions. This effect is significant when testing modulus and tensile strength from the previous results. Even within the same length scale, we can still that the distribution range of the mechanical properties very large, which would be influenced by its chemical composition and microstructure. What I aim to do is to find a relationship between these main influencing factors on the mechanical properties and try to build a model to describe the strength origin of CSH. The first thing to do is to accurately control the chemical composition and microstructure of CSH as a studying object. Instead of directly using the hydrated cement, the novel method I use is to synthesize the pure CSH via hydrothermal reaction. After 2 months reaction, the powders were dried in a specific state and then were put into 2 arch conditions to reach the true water content. Powders cured in 8% arch condition has no water in gel and capillary pores, and those cured in 100 arch condition are saturated in these pores. And then we use a high pressure to compact the powder into a pellet. It is worth noting that the superficial high pressure forms the bonding of interparticles and makes it possible to accurately control the porosity of the sample under different loading pressure. The obtained CSH pellets resemble the hydrated CSH. The various characterization techniques, including XRD, ICP, provides information on the chemical composition of CSH. The proton NMR gives the porosity of the multiscale strength testing techniques, including the hardness and the atomic force microscopy, provides a chance to explore the relationship among these 3 aspects. When we synthesize the CSH powders with calcium silicate ratio from 1 0.7 to 1.3. The XRD and ICP results show that there is no sign of calcium hydroxide in any powders and a very limited amount of carbonate phases, only in samples within calcium silicate ratio 1.1 and 1.3. The final calcium silicate ratio is close to the starting point input, combining the results of XRD and ICP. And the different compacting pressure provides different porosity of the CSH pellets. It is not surprising to see that higher compacting pressure will result in lower porosity, but interestingly, it is found that the influence of compacting pressure is much higher on porosity when CSH powders are in a drier state. From the SEM graph, there is no large pores and cracks observed. After preparing the samples with well-controlled calcium silicate ratio and porosity, the next step is to test its mechanical properties under different conditions. Superficial Rockwell hardness and viscous hardness are used to evaluate the macro and micro hardness of CSH samples respectively, with different calcium silicate ratio, water content, and porosity. In the two graphs, the x-axis is the initial calcium silicate ratio, and the y-axis is the hardness results. It is found that the higher porosity results in smaller hardness in two length scales. More water content has detrimental effect on hardness, and excitingly, we found an obvious effect of chemical composition on the strength. That is, higher calcium silicate ratio weakens the hardness of CSH. This phenomenon will be explained in detail by the experimental results of atomic force microscopy later. The changing regulation of hardness in macro and micro scale are almost the same, which reflects that hardness in two length scales are consistent using this sampling method. In order to explain the influence of calcium silicate ratio on the hardness, the surface forces in nanoscale were measured using atomic force microscopy. CS samples were put in two different arch conditions, and the AFM tip touched the surface and then is retracted. During the tip retraction, there is an obvious adhesion force between the CSH surface and AFMT, which is called capillary force. This force indicates the ability of water capturing of CSH surface. If the sample surface has a higher ability to capture water, the capillary force would be larger. From the box graph, we can find that CSH with higher calcium ratio has larger capillary force, and samples in higher arch condition has higher capillary force. It indicates that samples with higher calcium silicate ratio has a larger ability to capture water molecules. This provides a strong support to explain the influence of calcium silicate ratio on mechanical properties. When the dentate penetrates CSH, the plastic deformation is caused by the CSH particle sliding. Larger plastic formation is a reflection of smaller hardness value. The CSH surface with higher calcium ratio has more water content, which contributes to easier sliding between CSH particles. This is consistent with the results that CSH with higher calcium ratio has a lower hardness, no matter in microscale and macroscale. As for the influence of microstructure on hardness, these two graphs provide us with some new insights. The x-axis is the total porosity of the CSH pellets, and the y-axis is the superficial rockwear hardness and wicked hardness, respectively. All the data points under different conditions are put together. For CSH powders cured in 8% RH condition, higher compacting pressure will result in lower porosity and higher hardness. As for the samples cured in 100 RH condition, the change of porosity is not much from lower to higher compacting pressure, but the change of hardness is significant, which means that apart from porosity, there should be another important factor dominating the strength. We propose that this is the contact area between CSH surfaces. The SketchUp map shows that when the CSH powders cured in 8 RH condition, the higher compacting pressure will significantly decrease the total porosity. The denser microstructure results in larger strengths. However, as the CSH powders cured in 100 RH condition, the capillary pores and gel pores are all saturated. The existing water prevents significant decrease of porosity when using a larger compaction pressure, even though the contact points can still increase between surfaces, which also results in larger hardness values. Thus, the contact between CSH surfaces can be considered as a strength origin. Well, this work provides a novel method to accurately control the chemical composition and the microstructure of CSH samples, and we test the multiscale mechanical responses under different conditions. The relationship among mechanical properties, chemical composition, and microstructure are deeply discussed. Based on this method, a series of relevant work has been done and submitted. Please follow us if you are interested. Thank you very much for your attention, and I'm looking forward to your questions. Thank you.